Hello there, everybody. So this video will go over the second half of the practice test. So this is Unit 1 review video number 2. So again, we're going to go over the other part of the practice test. We're going to go in order, but we are skipping questions along the way. If you don't see a question in this video, that means it was covered in the previous video. Okay, so starting with number 1, this one says, which electron configuration represents a potassium atom in an excited state? So your first thing would be to check, well, how many electrons does potassium, or K, have? So potassium has 19 electrons, and we know that because that is the same as the atomic number. So remember, the atomic number is the number of protons. And then since we're talking about atoms, so neutral things, protons equals number of electrons. So potassium has to have 19 electrons. If something is excited, all that happens is that an electron moves location. You do not lose electrons, you do not gain electrons. So if we were to add up all of these, A gives you 15, B gives you 15. So right off the bat, it can't be A or B, because we have to aim for 19 electrons. Now, C and D both give you 19. So the way you figure out what the answer would be, it's talking about excited state. So choice C matches the periodic table. Now, if something is excited, it cannot match the periodic table. It has to be different. So that is what D says. D has 19 electrons, just like choice C, but what happened is that third shell, one of these electrons jumped up and moved to a different location. So first, figure out how many electrons it should have. Does it match the periodic table? If it does, that's what we call the ground state. And if it has the same number of electrons but in a different order, that is excited state. So your answer would be D. Moving forward, number 2. Number 2 says the weighted average of the atomic masses of the naturally occurring isotopes of an element is D. This is a straight definition question. An important definition, I should say. So one of the reasons you calculated the average atomic mass, or the weighted average, that gave you the atomic mass of the element. So remember, on your periodic table, if we're looking at carbon, it looks like this, 12.011. That is your atomic mass, and that is your weighted average of all the naturally occurring isotopes. Okay. So you might also see it as average atomic mass. Again, same thing. Okay. Number 3 is talking about isotopes. So remember, an isotope is the same element, and if you are the same element, you have the same number of protons. So protons don't change, but it has different neutrons. So if we look here, all the symbols say H, that means they're all hydrogen. So we can't use that to help us out. Now, in any example, the bottom number, that is your atomic number, and the top number, that is your mass. So if we're looking for an isotope, you have to have the same bottom number. Remember, if you change that bottom number, you change the element. So if we look at this, C has the bottom changed, so it can't be that. B has the bottom number changed, can't be that. D has the bottom numbers can't be changed, so it can't be that. Our only logical answer is A. Again, we have the bottom number, the atomic number is the same, but the atomic mass is different. And that's what an isotope is. Same element, different mass. Okay. Next says excited electron configuration represents an excited state for an atom of calcium. Excited state, calcium. Again, we're looking for calcium, which is Ca. If you ever forget or not sure yet what symbol is what element, if you flip your periodic table to table S, that gives you the name and the symbol. So calcium has an atomic number of 20. So that means we have 20 protons and 20 electrons. So that means our answer choice has to have 20 electrons. And if we add all of this up, A has 18, so it can't be A. B has 19, can't be B. Both C and D add up to 20. But again, we're talking about excited state. So it does not match the periodic table. If we're looking at the periodic table, it says 2-8-8-2. That is what choice D says. And that is that ground state. But the excited state has that electron jump up to a higher level. So right here, that electron that was in shell 3 bumped up to a higher energy level, making it choice C. Okay, so number 8. Number 8 says, which two notations represent isotopes of the same element? So remember, if we're talking about something that's the same element, we have to be, well, the same element. So we have the same symbol. And then you also have the same number of protons. And remember, that is your atomic number. And that is the bottom number of these things. But you have to have a different mass. So remember, if we think about it, if we have, any symbol, that number up there is the mass, and the number down here is the atomic number. So for this question, if we're looking for this same element, well, the easiest thing to look for is, do you have the same symbol? So N is nitrogen, so that's possible, same element. But if we look at B is N for nitrogen and E for neon. So if you have different symbols, that automatically has to give you a different element. Same thing for choice D, N and Ne, different element. Nitrogen is not the same as neon, and same with choice C. N and Ne are completely different, cannot be that. So the only logical answer is A. Moving forward, number 10. Number 10 says, given a list of atomic model descriptions, A, electron shells outside the central nucleus, B, hard indivisible spheres, C, mostly empty space. What is the order from the earliest model to the latest model? Now, if we're looking at this, when we're talking about the oldest model or the earliest model, that's the simplest thing. So the simplest one of these options is B. Which means we're going to start with B. That is the simplest, most basic thing we can be. So A and B are garbage. So now, what came next, C or A? So A is talking about electrons being organized in these shells, and C is talking about how the atom is mostly empty space. So the answer is going to be C. So if we think about it, Rutherford is the guy that said the atom is mostly empty space. He was the golden foil experiment. He said these positive alpha particles are going through an atom, and a few of them get deflected, meaning they bounce off of something else that has to be positive, but most of them pass right through, which means that it is going to be mostly empty space. And then a few years later on, Bohr and Schrödinger were studying, well, what is that empty space? And that is when Bohr had said that empty space is the electrons or kind of organized in these perfect shells. The model then continued going on from there, but in terms of these three choices, that is your best option. Okay, number 12 says the table below shows the atomic mass and natural abundance of two naturally occurring isotopes of lithium. Which numerical setup can be used to determine the atomic masses of the naturally occurring lithium? So if we look at our answers, because I haven't been looking at this yet, nothing is being divided by 100. So that means what they did, they had to have converted the percent to a decimal. So when you're doing that, yes, the other option is keeping it as is and dividing by 100, but our options do not have that. For choice C and D, you're dividing by 2. That is an absolute no. You cannot do that. So when you're taking your natural abundance and turning it into a decimal, so this was 7.6%, all you have to do is take that decimal point and move it 2 spots to the left. So 7.6% becomes 0.076. Again, 1, 2. And then if we look at 92.4%, that becomes 0.924 as a decimal. So then you're going to take, if you look at a different color, this, the lithium, you take your atomic mass, 6.015, times that decimal percent, which is 0.076, and we're going to add that to the other one. So we have the mass 7.016 times this percent, 0.924. A good bet is to always do this first and then check which one is the answer. Now, you don't see this written exactly, but you see A. So all A did, you see B. All B did was, it's the same thing, you're just switching. So this is like saying 2 times 5. What B says is doing 5 times 2. It's the same thing, the order doesn't matter. Now, a common mistake people make is choosing A. A would be right if it took everything and divided it by 100, but they did not, so that cannot be the answer. So it has to be B. Okay, number 14 says the bright line spectrum of an element in the gaseous phase is produced as A and B says protons move from different energy levels. Protons, they don't move, they're stuck in the nucleus. So it can't be that. So then we're talking about electrons. And again, if we're talking about the bright line spectrum, that's talking about the different lines in the pattern, kind of like that. So if that was each of these lines, where those lines come from? Again, we have to be talking about electrons. And those lines represent different wavelengths of light that was being released. And the only way light is being released is because the electrons are moving from a higher energy level to a lower energy level. So if you think about this, an electron was there. Let's call that blue dot. So energy comes in, hits that blue dot, it gets excited, so it jumps up. So now that blue electron moved up to a higher energy level. Now it doesn't stay there, it has to fall back down. And when it falls back down and returns to what we call the ground state, it has to release energy in the form of light. So that is where the light comes from. Okay. Number 16 says naturally occurring gallium is a mixture of isotopes that contain 60.11% of Ga69, and it gives you the mass, and 39.89% gallium-71, and it gives you the mass. What is the numerical setup that can be used to determine the mass of the naturally occurring gallium? So if you look at this, again, we can't divide by 2, so it can't be A. That is a bad answer. If you look at B, I don't even know what B did. Don't do that. Whenever you're taking a test, do not invent new ways to do things. If you're thinking to yourself, like, we've never done a question like this. We've never, did it in these steps. Now is not the time to start inventing new things. So again, if we're looking at this, here we can see that the percent was converted to a decimal. So remember, here are your percents. And choice D did not convert their percents to a decimal. So we don't even have to show our work for this one. We could just be like, well, it has to be C. Because either you convert your percentage to a decimal like D, or you leave it as is and divide everything by 100. But because D did not divide everything by 100, it cannot be that. So our only option is C. Okay, number 19. These are some of my favorite types of questions. What elements are present in this mixture? So here is your mixture, and here are 4 possible options, or 4 possible pieces that could make up that mixture. So one of the easiest things to do is to assign every line to a specific element. So if we go up and trace it up, these two obviously came from element X. Okay. If we look over here, element Z, there's nothing here. So if element Z was in the mixture, that means this line should have been there. But because it's not, Z is a no. So we can get rid of D, and we can get rid of B. So if we keep going, let's use a different color. This tracks all the way up to A. Right? This one tracks up there. Okay. This goes here, and with that one. Just momentarily confused myself. This one goes there. This one comes here. This one's there. This one matches up with 2 of them, and that one matches up there. So again, we could say it will be element A and element X, leaving it choice C. Now the reason it's not D, because D matches up a few times. If we look here, D has that double pair. If D was in the mixture, that double pair would be right there. But because it's not, D cannot be in the mixture. So in order for an element to be in the mixture, every single one of its lines needs to also be in the line. I don't care if you have 100 of them that match up. If one of them doesn't, it cannot be there. So if you're lining up every single line, it is almost guaranteed that you will get the right answer. Okay. Number 20 says each line in the spectra represents energy. Again, this energy has to be released, so it can't be A or B. Again, this energy is released when an excited electron moves from a high energy state to a low energy state, making it choice D. So the only way energy can be released if you have too much and you have to go back to normal. And the only way for an electron to go to a higher energy state is if it absorbs that energy. So C doesn't make any sense. D is the only one that makes sense. An electron releases energy in the form of light when it moves from a higher energy state to a lower energy state. That phrase is the answer to so many of these types of questions. Number 21. Number 21 says the table below gives the atomic mass and the abundance of 2 naturally occurring isotopes of chlorine. So the trick we had used in the previous question, just looking for the answer that looked correct, cannot work because all of these look pretty similar. And we can use it to get rid of some of the answers. So again, your percent, nothing is being divided by 100. So that means this needs to be converted to a decimal. So we can get rid of choice A and choice D, because again, these percents were not converted to a decimal. If those answer choices were divided by 100, that could have worked, but nothing's being divided by 100, so these answer choices cannot work. So if we're looking at it, we could say, okay, well, 75.76% as a decimal is 0.7576, and then 24.24% as a decimal is 0.2424. And remember, when we're doing this stays together, and this stays together. So if we write down our work, get a different color, get 34.97 times 0.7576 plus your 36.97 times 0.2424. And the only answer that matches both of them up is choice B. So B keeps this with this and that with that. What choice D did, they tried flip-flopping and making it look correct, but if it's actually not. So whenever you have these types of questions, it is a good idea to go ahead and write it down yourself and then see if your answer matches any of the other answers. Okay, number 22 says 40% of an element has a mass of 16 AMU, 60% has a mass of 18 AMU. What is the average atomic mass? So 40% is 16 AMU. And again, we can write it as 0.40. And then 60% is 18 AMU. And again, that can be written as 0.60. So because we've done the converting to a decimal, let's do it the other way. So you can do it both ways. Let's do 60 times 18. Again, keeping this together, plus the orange, 40 times the mass, like that. And if you're not converting anything, then you need to divide by 100. Or if you want, you could do 0.40, so that percent as a decimal, times that mass of 16, plus the other percent as a decimal, 0.60, times 18 AMU. Now everything is set, everything's converted, so you don't need to divide by 100. So now what's left is to plug it into a calculator. And if you're doing it like this way, plug everything into, you need parentheses, that is your best friend. But if we do it on a calculator, 0.40 times 16, this is 6.4, plus 0.60 times 18 is 10.8. 10.8 plus 6.4 gives you 17.2 AMU. And if you were to plug this into a calculator with the correct parentheses, you would also get 17.2 AMU. Now, a good way to think about this and kind of to check your answer, we know the smallest number is 16, then the small and the biggest mass is 18. So if we're averaging them together, we'd have to be somewhere in the middle of that. Now, because more of it is 18 and less of it is 16, it does make some sense that our answer is bigger, closer to 18 than it is to 16. So again, that is how you would do that, with both methods. Number 23. 23 says the bright line spectra of 4 elements and the mixture of elements are shown in the diagram below. Explain in terms of electrons and energy states how light emitted by excited electrons is produced. We could say when excited electrons return to a lower energy state, again, we're using those words, energy is released in the form of light. So this is a super awesome question. This pops up all the time as short answer questions and as multiple choice questions. This is a super, super, super awesome question. And again, when we did this in class, a lot of you were wording it accurately, but you're not saying in terms of electrons or energy states, so we'd have to not give you credit for that. So this is one that has a very, very, very particular way of answering this question. Okay, lastly, 24 gives you a whole paragraph about fireworks. Guess what? Doesn't matter. A lot of the times when you get these long paragraph questions, most of the time, not all the time, most of the time it's there just to confuse you. So here is where the question actually is. Explain why the electron configuration of 2711 represents sodium in an excited state. So we know it's sodium because if you add all these together, you get 9, 10, 11. Sodium, which is an A by the way, has 11 electrons because the atomic number is 11. So it's excited because one of that second shell should have 8 electrons. But what happened is something here got jumped up and moved a few levels. So we could say an electron jumped to a higher level. You could also say that an energy level was not full before another shell was created. If you said something about incomplete shells, electrons being jumped, it doesn't match the periodic table, it's not the ground state. All those things would work. There's a few different ways you could word this. So that is it for the practice test. Again, the questions that we didn't cover in this video are in the first video. Hope this helped. Bye.